Good morning and good evening.
To any other type of, into any other structure to monitor the status of the structure as well. And so many applications that I will not go over all of them. So since my talk is all about aerosol jet printing, so I will spend some time talking about the mechanism of the aerosol jet printing, how does it work, and what it makes the aerosol jet printing is attractive printing technique. So aerosol jet printing is a non-contact, direct write additive manufacturing technique where the material is deposited where it's needed based on a program toolpath. So the image that you see here to the left of the slide, this is the system that we have here in our lab at Binghamton University. So this is the 5-axis type of the system, meaning we have the ability to print in X and Y plane, and also we have the ability to print on a complex, irregular, non-planar surfaces utilizing the 5 degrees of freedom that we have in the machine. And also the system that we have, has 2 options for post-processing. So after we print, we need to do post-processing for whatever we print. So it has 2 options. The first option is laser module, and the second option is UV curing system. So when we print metallic structure, we need to solidify them. We need to form a conductive path. So we need to use either convection oven or laser sintering. Here in our case, in our system, we can use laser sintering to just selectively sinter the metallic printed traces without harming or affecting the substrate. And also in case of materials that are really sensitive to air like copper, we have a reducing gas environment around the laser module head, where we can shower the laser sinter traces with deforming gas and minimize or avoid the oxidation of the printed structure. So the other type of or the other option is UV system, where we can print UV sensitive material and cure them using the system that we have installed in the system. So I know it's a really complex and really it's complex system, aerosol jet printing, but think about it as your water hose sprayer that you can spray a very fine, very focused materials into the substrate. So the question is how the aerosols are generated. So we have 2 main mechanisms to generate the aerosols. The first one is pneumatic. The second one is ultrasonic. So what you see here in this cartoon to the center of the slide, this is the pneumatic mechanism, where we have a pure nitrogen that we applied into the ink that's loaded in the printer. This pressure or this pure nitrogen cause the ink to aerosolize, to form mist of material. And these mist of material or aerosols are transferred into what we call the virtual impactor. And inside the virtual impactor, if we have, and actually it does just filtering. So if you have a big particles, unfocused particles, it filters them out into the system filter. And then it transfers into the deposition head, where in the deposition head, again, don't know why my slides are moving by themselves, sorry. So in the deposition head, we have what we call sheath gas or sheath flow rate, which is again a pure nitrogen that we use to direct and collimate these aerosols into the substrate. And remember this term because we will talk about it later on when we talk about optimal process. So how do we decide which mechanism we should use? That's mainly depends on the ink that we are printing, and mainly on the ink characteristics like the viscosity, the solid loading, and the particle size. So here in this slide, I'm showing you from the design into the part, the entire process. So the design for printing can be done either in a CAD design, in any CAD software, or in any PCB design software like Eagle or Altium, and then we convert the design into the CAD drawing. And then we are using an add-on in the CAD software that we have. It's supplied by the printer manufacturer, which is Optomic, to generate the toolpath. And then the process. So the process, we need to decide so many things based on what we want to print, where we want to print. Do we want to print a very fine lines, or do we want to print a big and millimeter size structures? Based on that, we decide what parameters we use, what nozzle diameter we use, and what system actually we use based on the type of ink. Do we want to use ultrasonic or pneumatic? It depends on the ink that we want to use. And then the part. So the printed output is a conformally printed, high resolution, and it can be with a multi-layer circuit, as we will see in some of the examples in the few next slides. So here I'm showing you around 8-inch long, 1-inch wide broadband antenna. It's part of an ongoing project that we are working on right now. And we are printing this antenna using the gold on 3D printed additively manufactured ceramic substrate, and then we fire and process the printed part at 850, and eventually we are forming a broadband antenna that operates at 2.4 gigahertz and can sustain 750 C without degradation in the performance, or without affect the performance. So with the aerosol jet printing, we have been printing a lot of materials on a very wide variety of substrate. So we have been printing conductors, insulator, resistive, or semiconductors material, and they are in a very different shapes. They can be nanoparticles, they can be nanospheres, they can be flakes, microflakes, macroflakes. As long as they are within a certain size, we can aerosolize and print them. Regarding the substrate, we can print on any substrate required to be printed. And also for the design, we have freedom in the design as well. So we can print a very simple traces, and we can print a very complex and highly design. Okay, so here I'm just showing you some of the examples that we have been working on. The first one, you see silver traces or silver design that printed on paper substrate. This is and also laser sintered using the laser system that we have. And this was part of a sweat rate project. And also we have been working with Lockheed Martin on fabricating devices that require vias. So we were able to print and fabricate vias in a 10 micron thick polyimide substrate. And also with collaboration with Lockheed Martin, we have been working on their developed ink, which is carbon nanostructure, and we have been printing that ink on a wide variety of substrates. Here I'm showing you the PET substrate, which is the polyethylene tetraphthalate substrate. And also to show you the quality of the print that we have been achieving based on our optimal process. You see here where the pointer is a silver trace on polyimide substrate that looks very nice, clean, and nice. And also we have been printing on other substrates like LCP. So here in collaboration with Lockheed Martin, we are printing UV dielectric material, and then we are printing also a silver trace on the LCP substrate. Not only conventional inks, but also we have been printing precious metals like gold. Here I'm showing you a printed structure on gold, printed with the gold on ceramic substrate, thick ceramic, and also on a flexible ceramic. And that's what you see in this image that I'm pointing with the pointer. And also we have been printing a complete metallization circuit. So that's what you see here. It's a photoresist printed on piece of FR4. And after printing the photoresist, we etch out the copper and then strip the photoresist. And eventually we have a metallization circuit that we use for a heart rate monitor project. And also other inks like platinum. So we have been printing nanoparticles, platinum, and microflakes and macroflakes, platinum ink on ceramic substrate. And also recently we have been working with inks that we did not think at some point that we will be working on. So we are adopting inks or materials that ceramic decoration industry is using to decorate ceramic. They are gold and other type of materials. So we are using those materials to print electronics component. So in the few coming slides, I will be talking about a complete devices or cases that we have been working on in our lab. So remember in the introduction, I talked about the structural health monitoring as an emerging opportunity for flexible hybrid electronics to be applicable in, right? So let's picture the following scenario. So you have here two pictures. These represent the wind turbine blade, GE wind turbine blade. It's about over 100-meter long, and it has a very wide diameter, and it's expensive, and it takes a really long time to fabricate something like that. So what we wanted to do, or what we are working currently with Lockheed Martin and Georgia Tech and GE Global Research, to develop a patch or sensors that we can insert or embed it into this wind blade and monitor the status of the fabrication. And also not only the status of the fabrication, but also during the operation. So think about these power generation wind blades are installed in a very different places that you can reach easily, places that it's not easy to reach, and you need to keep checking the status of these plates, right? Otherwise, it will cost the company, will cost the community a lot of money. So what also wanted to do, we wanted to embed it also a patch of sensors inside this wind turbine blade, okay, that the operator can just go there, point with the reader, and see what is the status of the blade. Does it require maintenance? Does it get degraded? What is actually the status of the wind blade itself? So as a researcher, as an R&D team, we always started with the prototyping, and we started in the lab. So we started by printing with the aerosol jet printer. We're printing a patch of antenna. Here in this case, it's a Vanata array antenna. And then we are embedding the printed structure into a composite. We have been working with the two different composites. We have been working with carbon fiber and glass fiber composites. And then we are mimicking the scenarios that will happen during the manufacturing and during the operation status. So, for example, one of the tasks that we have been working in to do a mechanical test, wide variety of mechanical tests, including bending, stretching, cycling, compression, and see how we can correlate between the mechanical stress or the mechanical strain that we are inducing into the composite, which already has the embedded sensor on it, with the RF performance of such a printed structure. And we, for example, here as an example, when we have a 0 micro strain, there is no strain on the composite, we are reading the maximum power generated by the printed antenna that's already embedded into the composite. And if we apply, let's say, a 3000 micro strain, what we are getting is slightly shift in the power, and that makes sense because our patch antenna got smaller and that changed the performance. So by knowing this knowledge, we are correlating and creating a transfer function that allow us to embed these sensors into the composite and then just go there with the reader and read whatever the state of the blade based on the developed process. So another success story, and actually quite good work we have been doing here, is to fabricate. So as I mentioned in the beginning, with the aerosol jet printing, we can print a different type of materials. We can print multi-layer circuit on any substrate. So here we participated in Department of US Navy mini challenge. So the US Navy released a consortium, which is additive manufacturing for technology protection. And they required the members to develop or create a 3D printed articles. Everything is printed. The substrate is printed, and also printed resistors and capacitors that have specific values. So in this work with collaboration with our colleagues in Lockheed Martin, we participated in this mini challenge. So for the resistor, so before doing this one, we went back into the screening experiments and we printed the carbon nanostructure that developed by Lockheed Martin with a different line width, different line thicknesses and structure to just have an idea and design if we want a 1 kilo ohm resistor, what should be the ideal dimensions for the resistor. And then based on that, we were able, okay, now if we print like 10 millimeter long line with the 2 millimeter width and this amount of thickness, we will be able to get 1 kilo ohm resistor. And that one task was done. So the other task was creating a capacitors that have 1 nanofarad. So we adopt the metal insulator, metal design for fabricating the capacitors, and the cross section is shown here on the bottom of the slide. So as you see, we have the big plate out of the silver printed using the aerosol jet printer and then cured at 200 C, or actually here at 150 C. And then we have a dielectric material in between. And then on the top, we had a big plate to form the capacitor, and then we were measuring the capacitance. So one of the things that we have been learning here in this project is when we were measuring with the top metal, just a solid metal of the silver on the top, we were getting short, and we did not get 3 of them are working. So what we did, we think about it for some time, and then we say, okay, let's divide the top metal into a bunch of small plates, and then we connect them in parallel, and then we measure. If we see any short due to the pinholes between the top and the bottom metal, we just remove it, rework it, and it did work. And we submitted our article to the organization community, and we won the first place. And that was a good ending for the last year, 2020. So also with the aerosol jet printing, we can print in any surface. It doesn't matter to, it doesn't require to be in an X and Y. It can be any shape, irregular shape, complex shape. We have the capability to do that. And here I'm showing you some of the examples, many examples we have been doing to utilize our 5-axis capability in demonstrating printing on a highly non-conformal substrates. So the video to the left and also the images that you see here, it's for silver printed with the aerosol jet printing, 70 micron line width with a 3 micron thickness on a sinusoidal wave shape to demonstrate the for the real product or the real task that we have been working with GE Global Research. And also what you see here also in the center of the slide is printing a silver on a 3D printed ceramic dome using a wide nozzle head of the printer. And also we have been printing as well copper. As you see here, copper printed in a like a cone shape in a collaboration with our colleagues at Lockheed Martin. So another a good story to demonstrate that we have been doing a very good job in aerosol jet printing to help the community and to help our collaborators is using aerosol jet printing for repair damaged chip. So in collaboration with IEC, it's a failure analysis and reliability center in our university. We have been getting chips, damaged chips, can be a memory, can be any chips from the National Transportation Safety Board. They have some defects. They are broken. They are missing some components during the plane crash accidents, and they were asking, "Can you repair these so we can read them and extract the information that we want to know about what happened, what was the failure before the accident?" So I'm showing here 2 examples of many examples we have been working with. So this image that you see in the center of the slide, it's an X-ray image for the memory module that's shown to the left. And as you see, we have 2 wires that are coming out of the die, and there is no connection between these wires. So the task was to print a pad that connect these wires And maybe you will think it's a simple, but it's not that simple. So think about 100 micron by 100 micron pad that we need to print precisely to connect these two wires. And also it requires to have as thick, the same thickness as the other pads on the other chip. So it will be able to sit on the reader and extract and be readable from the machine. And we were able to do that, and it was success repaired, and that's what you see in the image to the right. So the other example is a damaged chip where we required to print a less than 50 micron line width to connect these broken interconnects without shorting them. And that's also, we did it, and we sent the repaired part to the NTPS, and they were able to read it. They were happy, and we were happy. So all what you have seen so far, it's not just, okay, we have this task, let's go to the lab and start working. It's a result of deep understanding and extensive experimentation on the aerosol jet printing process to have an optimal process, an printing process, and optimal post-processing. And that's what I will show you in the coming few slides. So let's start by looking into the center of the slide where we have the fishbone diagram that describe or summarize the key parameters that could affect the printed structure using aerosol jet printing. So we have so many variables, so many factors, either can be due to the ink, the substrate, the printing environment, the printing process, and so on. So what we did, we have been studying most of these parameters and studying how these parameters could affect the performance of our printed structure. So to just give you an example, what we did, we picked two substrates. These substrates are LCP, which is liquid crystal polymer substrate, and Kapton. These two substrates are very common in flexible hybrid electronics application, and in conventional, actually in the conventional electronics industry area as well. And we printed RF components, which are transmission lines. And then we studied the effect of most of these parameters. And our measurement, our output was to see how the parameters could affect the thickness, the width, the surface roughness, the electrical resistance, and the microstructure of the printed traces or transmission lines. And then at the end of this study, we printed microstrip lines on Kapton and LCP, and we measured these printed microstrip lines up to 40 gigahertz based on the recommendation and the optimal process that we have. And the results were kind of satisfying. So I'm not going to go over all what we have been doing regarding defining an optimal process for aerosol jet printing. I will talk about just the effect of the sheath flow rate. Remember in the very beginning when I talked about the aerosol jet printing mechanism, we talked about sheath flow rate, and we said that the sheath flow rate is the amount of the flow that we apply to focus and direct the aerosols into the substrate. So let's see how the sheath flow rate could affect the characteristic of the printed traces on LCP and on Kapton, and that's what you see on these images. So starting with the resistance. So let's start with the resistance. So at 20 SCCM, okay, you see Kapton has higher resistance than LCP. However, if you look into the thickness, which is the other two graphs to the left, the thickness and the width, you will see Kapton is thicker, Kapton is wider, and that violates Ohm's law, where the thicker the wider should be higher, lower resistance, right? And that's because of the substrate. So we have our substrate, which is the LCP. It has a higher surface roughness than the Kapton that allow the nanoparticle to become more dense and pack on top of each other, and that resulting in decreasing the resistance regardless the geometry of the trace. Okay, and the same thing with the at 40 and 60. However, at 80 and 100, now we have a high sheath flow rate that overcome the effect of the substrate. And what is dominant here is the geometry of the printed traces, and that what you see here, you have a correlation, a good correlation based on Ohm's law between the resistance and the thickness and the width, okay? And also another note or observation we can draw from this experiment is you see at 80 SCCM and 100 SCCM, you started seeing the lines are not clear, right? Are not clean. So there is what we call overspray around the printed lines, and that significantly affect the RF performance, the sensitivity of printed sensors using these parameters. And that's because of you have a high sheath flow rate that convert your flow into a turbulence, and it's not well controlled, not well focused. So as you see here, we have a good optimal process based on just investigation on the effect of the sheath flow rate. So after we print, we have to solidify. We have to convert what we're printing as a liquid into a solid. So we have to achieve some conductivity to be useful in any application. So there are several techniques to do post-processing. Here we are talking about convection oven and laser sintering. So we printed some of the lines and then we sintered them in a convection oven for 1 hour at different temperature, starting from 150 up to 300 C. And we cannot go beyond 300 C because of the substrate. So our substrates are flexible, are sensitive, polymer, plastic, that's sensitive to the temperature. They will be, they will burn or they will deform if we go higher than 300. And now everyone is looking for low temperature processing because that's what is required from practical point of view. So as you see, the resistance goes down, and that's something expected because as the temperature goes higher, we have more energy to print the nanoparticles in contact with each other more. And if we want to get more conductive lines, we need to go higher in the temperature, and that's impossible. We cannot do that. So we are utilizing the laser system. So by using the laser system, we are selectively center the metal, which it doesn't matter how high the temperature can be, without harming, without affecting the substrate. And that's what you see here. When we started at 100 milliwatt laser power with a 5 millimeter per second scanning speed, we are getting much lower resistance as if we centered our traces in a convection oven for 1 hour at 300 C. And the resistance keep dropping as a function of the laser power as well. So to just give you a better image on what happened to why the resistance is going down as a function of the laser power, let's look into these SCM images that we take for printed structure on flexible substrate that we air dried. So after we just dry it, we sent it out for SCM or sintered in a convection oven at 200 C for 1 hour, or use the laser system to sinter it at 600 milliwatt and 900 milliwatt. So as you see from the air dried samples, we have just individual nanoparticles. The organic content is still there. So maybe it's conductive, maybe it's not conductive. In this ink, it's not conductive. It needs high power. It needs some energy to make it conductive. So at 200 C, we started seeing the microstructure coming, the nanoparticles come in contact better than at air dry. Now, if we use 600 milliwatt, or if we use a laser sintering, we started seeing extensive nicking and particle size and fusing of the nanoparticles. Because we are engineers, we like numbers. What we did, we take these images, we use MATLAB to extract or do image processing and see how the particle diameter is changing as a corresponding to the power. And that's what we are seeing here as a good correlation between the average particle size and also the SCM images and the resistance. So moving to another topic, which is the current carrying capacity of aerosol jet printed traces on flexible substrate. So what we wanted to do as a motivation for this study is to study how much current we can apply into our trace without operational failure. So when we apply a current, there is by mean of Joule heating, there is a heat or there is a temperature generated by the current, right? And we have a flexible substrate, sensitive substrate. So we wanted to know what is our limitation, what's really happening there, and what is our window of working. And we studied the literature. There are a very few papers talked about this topic, but not as deep as what we did. So to study the electrical performance of any conductors, we start by studying the thermal coefficient of resistance, which is a material property where we want to know if we have a conductor, we heat that conductor, we need to know how much resistance we are getting per degree Celsius. That will help in the design and in the manufacturing as well. So what we did, we printed several lines with 100 micron line width up to 500 micron line width. Okay, this is the test structure that you see here, 1 inch long. And then we started by doing one experiment. So just put your samples in an oven, heat it from room temperature to, let's say here, 250, and see what will happen to the resistance. So as you see here, we have two regions. The first region is we have fairly linear relation between the resistance and the temperature. And that's, we call it temperature dependent. And then at some point, we start see the resistance goes down, which means there is something happen to the microstructure. Your microstructure now starts to get or to change because of the high temperature. So if we limit our, let's say, if we expose our traces into temperature up to 150 or 140, and then we heat it up, bring it back, you will see there is a complete recovery in the resistance, which means the change in the resistance that you see during the heating, it's completely recovered. And also, if we use this linear region or linear relationship to calculate the TCR, which is the thermal coefficient of resistance, we will end up having a value that's much lower than the bulk value. So our bulk value is 3.8, what we are getting is 1.5. And that's why, because of the nature of what we print, we are printing porous structure that have opening and porous that add more resistance into our traces. Now, how we can bring the microstructure to be closer to the bulk? Remember what we talked about, heating at higher temperature and using the laser. And by using that, we were able to get more like higher value closer to the bulk. So again, I just mentioned when we apply a current, there is a heat generated by the current, right, based on Joule heating. So what we did to experiment that, we have an IR thermal microscope. That's what you see here in this image, okay? And then we are applying a current, we are measuring the resistance and recording the temperature generated by the current. And this is the results, what you see in the center of the slide. So if we just, the temperature versus the current, that's something expected. As the current goes high, the resistance, the temperature goes high. However, the resistance versus the current, that depends on how much current you have. So you see we have three regions. The first region that we just talked about is temperature dependent. The second one is centering, where the current starts to induce centering. And the third one is a stable, and after that we have a failure. And that's what you see here also in these thermal images and optical images of the printed traces during that experiment. So I know I'm running out of the time, so I will go over the last part very quickly. So what we have been, so this is an ongoing project with Lockheed Martin and GE Global Research, where we are adopting our understanding of flexible hybrid electronics processes to fabricate electronics that could handle or survive high temperature environment. So think about a very high temperature application like geothermal logging wells, aviation, power generation, hypersonic vehicles. Such application, the temperature easily go above 500 C. So we wanted to leverage our understanding, our capability of 3D printing to fabricate electronics that could survive such high temperature. So we started by the literature, we digged into the literature. There is a very few studies in the literature for people who use 3D printing and taking the advantages of 3D printing to fabricate electronics for high temperature. Here I'm listing just two of them. The first one is from University of Buffalo, where they developed their own ink and characterized up to 500 C. The other studies from a project funded by the Department of Energy for Open University and GE, where they developed fabricated electronic component and studies the performance up to 350. So there is a gap in the literature and there is a need for such a work. So what we did, we started by identifying inks and substrates. So for inks, looking into the market, there is no ink for aerosol jet printing that could handle more than 350. So we started looking for alternative inks and work on them, change the or modify the ink to make them printable. Okay, and then for the substrates, we have been working with a conventional fabricated substrate commercially available from Acumet. It's a ceramic substrate, and also we have been working with substrates that 3D printed by our collaborator. And also because we are a flexible community and we like everything to be flexible, we work also Corning ceramic flexible ribbons. We use both of their technologies, the 40 and the 80 micron. And we fabricated a very wide range of electronics components, either interconnects, RF components, capacitors, and we developed processes for electronics packaging, including a surface mount, flip chip, and embedded chip packaging type of electronics. And we characterize them at different temperature up to 750. So I will go here quickly over one of the tasks that we have been doing. It's printing gold on ceramic substrate, and then check the resistance at high temperature up to 750 while it's being aged up to 100 hour or more than 100 hour. So as we mentioned in the previous slide, the resistance will go up as a function of the temperature. However, and that's what we saw in all of the materials. However, at the peak temperature, here 750 and 500, we started seeing a different performance, different behavior of different material. Material A, which was shown here in the first figure to the left, it shows that the resistance is stable, nothing is changing. And if the temperature goes back to the room temperature, the resistance will completely recover. The other material is start to go up. So the resistance start to go up. And once the temperature go back to the room temperature, it doesn't completely recover. It goes higher than what we started with. Other materials like gold at 650, after 10 minutes, they just evaporated and become discontinuous lines. Platinum at 750, after 12 hours, they become open. And that we believe because of forming a new material, new layer. It could be oxidation. We are currently working on this phenomena to see what's really happening there. So also, during this project, we have been doing adhesion. So it's good to have printed structure that conductive, that survives 750 or higher, but we need something that really stick to the substrate. So what we have been doing as an example of the adhesion, we have been assessing the adhesion of the printed structure into the ceramic substrate. Here I'm showing you, we printed gold structure on flexible ceramic, and then we are conducting the a stud pull test. So it's just a stud that coated with the epoxy, and then we just cure it, and then we try to pull the stud and see what is the maximum force required to do that. So the results are summarized in this box plot that you see here at different temperature, after aging at different temperature. In general, we had a very nice, for this material, we had a very nice and excellent adhesion. And you see the studs after testing, they look clean. Nothing is there, meaning the adhesion is perfect. From other experiments were to check the bendability of the substrate and also the bendability of the printed gold there. So we printed gold in two different structures that you see here. And we did a bending over mandrel for 1,000 cycle in a different mode. And we monitored the resistance after aging at different temperature up to 750. And that's what you see here in this video and in this graph, where the resistance actually stays stable. There was no change in the resistance or significant change in the resistance after testing. So the last slide is, in any electronic system also, we want RF component, right? So either could be antenna, or it could be a transmission line, or any other type of RF component. So what is important is to know how the dielectric constant is changing as a function of the temperature. When you buy any material, the dielectric constant is specified at specific temperature. So we wanted to know how it's changing. So this is our setup, what you see in the image to the left, where we have a tube furnace, and then we have a sample inside it, and then we are hooking two cables, silicon dioxide cables, into our vector network analyzer to measure the S parameter or the scattering parameters. And then we extract the dielectric constant and the loss tangent of the printed transmission line using a well-known approach called a phase shift method. And we can discuss about it more if anyone is interested. And then at the end, we have in the y-axis, we have a dielectric constant. In the x-axis, we have the temperature. So as you see, the dielectric constant is pretty stable with slightly increase up to 400, where everything starts to change. You have the substrate start to be more conductive, and also the ink start to be more resistive, and so on. So that's what caused the sharp increase in the dielectric constant at 450. So as a conclusion, flexible hybrid electronics offer low cost, fast, conformal, and high throughput electronics. And also we have been demonstrating the use of aerosol jet printer as an emerging technology for printing and different electronics that can be used for any application. Thank you very much. Sorry for the long presentation, and I'm happy to take any question.
Thank you. Thank you very much, Mohammed, for the excellent presentation. Definitely very comprehensive and cutting edge research. So we definitely appreciate you covering both breadth and depth in various areas in your research work with Dr. Pollux. Thank you. At this point, we will open it up to any questions.
Professor Mohammed, I have a question for Mohammed Alhendi.
Yes, please.
Yes. Hey, very good presentation, Mohammed. I liked it. Very comprehensive. I want to know whether we could be achieving printing of a complete electronic device using 3D printing. Do you think that is possible? Something similar to, for example, printing a book. We can download a PDF and print it. Something similar to that, do you think it might be possible to print an electronic device?
Yeah, so that's a good question. So, I mean, the short answer, we can, but it will not be performing as we want. So that's the innovation in this industry, is to take the advantages of the printing, because it's easy and fast and all of the things that we talked about, and also take the performance of the silicon-based or the rigid components made of the silicon. So we need the performance from there. Otherwise, we can print transistor, but it will not perform as you have a silicon-based transistor there. So it's possible, but it will not perform as the conventional microelectronics thing. And I think that's also what Professor Pollux showed in his presentation about the Arduino, printed Arduino by Nextflex, where they printed everything except the die. They used a bare die, thin die, and integrated into the printed circuit, and they were able to have the FHE Arduino that's flexible. Most of it is printable, but not all of it.
Thank you.
Hi, Mohammed. It was a nice presentation. Thanks for it. And I have a question. I was working on TST components and SMD components. Now the complete shift. I can see the complete shift. Like how can we manage the power things in these components, and how do we debug if something goes wrong with some component? How do we debug it?
Okay, so if I understand, your question is about power, right? How we power such a components or such a integration of components with a printed circuit, right?
Yeah.
Yeah, that's really a great question. And unfortunately, we have to use, maybe my experience is not a lot to talk about it, but people have started to print batteries to power such electronic circuit, but still there is a limitation. So definitely you still need to use the conventional batteries that we know in order to power the any electronic circuit that's fabricated with this technology. And also the consideration that we need to talk about is what I mentioned in the at the very end of the slides for the current carrying capacity. So that will help you understanding how much power you need in order to power any circuit. Not sure if I answered your question, but
Yeah, thank you. And what about the testing of the components? There are say some 10 to 15 components printed on a board. Say, let us suppose. Okay, so if something goes wrong with one particular component, see in the regular PCB boards or something, we can have multimeter or some kind of gadget where we can test where something went wrong. So in these boards or these components, how do we do that?
I mean, it's the same way. So I mean, we are not changing anything except just we have a printed rather than plated interconnect. So it will be the same. You have a test point to go there and test your connection and debug your circuit.
Okay, like how we can do for discrete components, we can do the same way.
Yeah, can you explain it more? I'm not sure.
Yeah,
If
like
I...
how we do for discrete components.
Mhm.
The same way we can do for these components even.
So, okay, so what we are doing, we are printing the interconnect and we are integrating the component, either discrete components, passive or active components into the printed circuit, okay? So everything will be same as you do with the conventional microelectronics, troubleshooting, failure analysis, and technique. It's just a special handling here, special processing because you have everything is flexible.
Thank you.
Thank you, Mohammed. Any other questions? Again, we'll probably have time for one more question. Feel free to.
Hi, this is Steve.
Yes, Steve.
Ganya. Hi, Mohammed. Very nice presentation. A lot of good data. Hey, I was interested in the transmission lines where you're measuring insertion loss over frequency, and I wondered, how does it compare, the printed lines compare to conventionally etched copper? And also, how can you get the printed lines to perform as well as the etched copper lines, specifically for the RF frequencies that we're doing?
Yeah, so Steve Gani is one of our amazing collaborators that we work together on so many things. So, I mean, so again, so we have been testing printed RF components. They are comparable somehow, but not exact as the performance of the etched copper. But we were able to get them by doing an optimal printing, have a nice line, clean line, same as the design in terms of the thickness, in terms of the width, in terms of the surface roughness, and also to have a highly conductive traces. So we have been doing that before where we just oven center traces or transmission line, and then we measure the RF performance, and then we do a laser sintering where the conductivity goes up significantly. That enhance the performance of the printed microstrip lines if we use a laser sintering. So, I mean, in simple words, is just try to make the printed line as clean as possible, as the same as the design, because I mean, one of the issues that we are having is the repeatability. So how we can, and the reproducibility, and how we can get exactly what we design, same as what we print. So if we are able to get what we design with the clean lines, minimal surface roughness, and highly conductive, we could achieve a good insertion loss.
Okay, yeah, that's there's a lot of things that go into the insertion loss, and I was just I wanted to hear how you were addressing them. You know, the voiding, the surface roughness, the geometry of the line. You know, all these things sort of go into the loss, and you know, ultimately, the closer we can get to the performance of actual etch foil, the more useful these structures will become. So, thank you.
Thank you. Any other questions? I don't see any questions in the chat. I see a lot of great feedback about your presentation in the chat, Mohammed. So congratulations for doing such an excellent job. Okay, so Mohammed, again, thank you very much for joining us today on behalf of Binghamton University and VIT. Dean Vasudevan and I would like to thank you for your contribution to our seminar series. We have definitely enjoyed having you, and we appreciate you spending time to explain your work and share it with our colleagues, both here in the US and with our colleagues in India as well.
Yep. Thank you, Professor Kasauna, and
Thank
thank
you.
you everyone for attending. Thank you.
Thank you. Thank you. And before we conclude, yes, Dean Vasudevan, go ahead.
Thank you, Professor Mohammed.
Okay, so before we conclude, I just want to remind everyone about next week's talk. Next week, we have Dr. Fatima Patham from VIT. She will talk about design of lightweight aerospace structures using topology optimization. So if your schedule allows, please join us next week. Again, it will be on Thursday at 8:30 a.m. Eastern Time and 6 p.m. India Standard Time. So please feel free to share this information with your colleagues, friends, students, and scholars, and hope that you will join us again next week. And as a follow-up, I will be sending the recording of this morning's presentation, or this evening, depending on where you are, with everyone, and with the registration information for next week's presentation as well. So thank you again to everyone for joining us today, and thank you again to our speaker for the great presentation.
Thank you very much, Professor Mohammed, and for your talk. Thank you very much.
Thank you.
Have a nice day. Thank you. Thank you.
Thank you, everyone.